So here we'll talk about vector spaces and subspaces. And we'll start with the vector spaces. So a vector space is a non-empty set V of objects, which we're going to call vectors, together with two different operations, addition and scalar multiplication. And they're subject to the following axioms. So there's 10 axioms here, and it is a very long definition. I don't expect you to memorize all 10 of these. I'll go through the definition and talk about a little bit about each one. And then I'll go in and define some of our main vector spaces that we're going to be dealing with. So we'll prove that they're vector spaces, and then we won't have to worry about this definition again. So number 1, closed under addition. Basically, if the two vectors are in the space, their sum should also be in the space. Additive commutativity, the order of addition shouldn't matter. Additive associativity, I should be able to move parentheses around in my addition as much as I want. And additive identity, this says that there's a zero vector. So there's a vector such that u plus 0 is equal to u. The additive inverse, for every u, there's a negative u, such that I can add them up and get to the zero vector. Closed under scalar multiplication, if I multiply by a scalar, I should still be in the set. 7, I have the distributive property. I can distribute a scalar over a sum of vectors. 8 is distributing a vector over the sum of scalars. Number 9 says I can multiply by the scalars in any order that I want. And then 10, the multiplicative identity. 1 times u is u. My first example of a vector space is Rn for any value of n. So R2 is a vector space, R3 is a vector space, R4, etc. So I'm not going to prove all 10 axioms for this, mainly because it's all been done before in previous chapters. We've talked about addition on vectors and we've talked about scalar multiplication. The next example is the zero space. So this is the space with only one vector, 0. We define addition exactly like you would expect. 0 plus 0 is 0. And any scalar times 0 will be 0. So once again, I'm not going to check all 10 of the axioms because they're pretty easy. The next example. So this time, our vectors are going to be objects of the form u sub 1, u sub 2, u sub 3, u sub 4, forever. We define component-wise addition and scalar multiplication. And this is a vector space. So basically we've talked about R2, we've talked about R3, we've talked about R4, which is basically just a vector with that many entries. So for instance, R4 is a vector with 4 entries. This is R infinity. It's an infinitely long vector. You can also think of it as a series. If you're familiar with series and sequences, it can be thought of as either a series or a sequence. The next example, let's consider the space of all 2 by 2 matrices. We'll use the usual operations of addition and scalar multiplication. And this is a vector space due to the properties of matrices that we've discussed throughout the semester. And it's important to note that nothing's unique about 2 by 2. In general, if we want to talk about the vector space of a certain size matrix, m by n, we denote it by m sub m by n. The capital M for matrices. And so as long as you consider a single size, we can define it as a vector space. My next vector space, let's consider all real valued functions defined on the interval negative infinity to infinity. So basically anything that's defined over the entire interval. We define addition and scalar multiplication just as you normally define addition and multiplication on functions. So I won't talk about all of the axioms here, but I will talk about a few. First off, since each function is defined on the entire interval, adding the functions will not change the domain. Multiplying by a scalar will also not change the domain. So it's closed under addition and scalar multiplication. So we have axioms 1 and 6. So axiom 4 requires a 0 function. We'll just define this as the function f of x equal to 0. Axiom 5 requires an additive inverse negative f. So we'll just define this as -1 times f. And this is obtained by a reflection across the x-axis. The rest of the axioms will follow from properties of real numbers. And this vector space is defined as f (-infinity to infinity). It's called the function space. The f is for function. There's nothing unique about this interval. Basically, if I define an interval, a to b, and I consider all real valued functions defined on that interval, I will also get a vector space. For my final example, I'm going to do a strange vector space, just to show you what all goes into proving something is a vector space. So here, my space V is the set of all positive real numbers. We'll define these operations. If I say u plus v, what I'll really mean is u times v. A scalar times u is really equal to u raised to the r power. The first of these, since u and v are both positive, u times v is still going to be positive. So that means it's closed under the addition. The second one, u plus v, actually is u to v. And then we know these are just positive real numbers, and the order of positive real number multiplication doesn't matter. So that's vu, which is by definition the vector v plus the vector u. For number 3, u plus v plus w. Well, v plus w just means v times w. Adding in the extra u means we're going to multiply that by u. The order of parentheses doesn't matter in regular positive number multiplication, so we can move it around. We can then break that up to u times v plus the vector w, and u times v means u plus v plus the vector w. Number 4 says we need a 0 vector. First off, the number 0 actually isn't in this set since 0 isn't positive. However, what we really need is a vector that I can add to u and get u back out. So I need u plus this vector to be equal to u. And that's 1. 1 plus u, by definition of this vector space, is 1u, which is just u. So our, what we usually call the 0 vector, in this case will be 1. Number 5 needs an additive inverse. So now we need a vector that we can add to u and get the 0 vector, which in this case is 1. And you can see that 1 plus 1 over u, by definition of the vector space, is u times 1 over u, which is 1, which we are calling the 0 vector. Number 6, multiplying by a scalar really means to raise to an exponent. And if I raise a positive number to an exponent, I get a positive number. So it is closed under scalar multiplication. The next is the first of the distributive properties. By definition, u plus v means uv, and multiplying that by a scalar, it's the same thing as raising it to an exponent. Properties of exponents say that that is urvr, which, by definition of our operations, is the vector u to the r power plus the vector v to the r power. Using the definition of scalar multiplication, we get ru plus rv. Number 8 is the other distributive property. R plus s times the vector u. By definition of scalar multiplication, this is ru to the r plus s power. Properties of exponents say that this is ur times us. Definition of our vector addition says that this is u to the r plus u to the s. And definition of our scalar multiplication gives us ru plus su. Number 9, the s times u means u to the s power. Multiplying that by a scalar means we're going to raise u to the s to the r power. Properties of exponents give us that this is u times r to the s. And by definition of scalar multiplication in this vector space, this is rs times u. Finally, 1 times u means raising u to the first power, and anything to the first power is itself. So I know that this is a very strange vector space, and people tend to have problems with it. You may not completely understand everything I've done here, and that's fine. Usually, it's a little bit more understandable once you realize that these are actually properties of logarithms, so it's not completely strange and foreign. But the main point of this example is to kind of show you what goes into proving something is a full vector space. So most of my examples, I'm pulling theorems from other classes or previous chapters, so I'm not going to sit here and prove them. But in general, it does take a lot of work. Here are 3 properties of vector spaces. So these 3 things are some things that seem like it would be fairly obvious, but it actually takes a lot of work to prove them. The first, for every vector u in the vector space, 0 times u is equal to the 0 vector. The second, for every scalar r times the 0 vector is equal to the 0 vector. And then third, for every vector u in v, negative u is equal to negative 1 times u. So like I said, there are things that seem fairly obvious, but they take a lot of work to actually show. I will not prove them here, but if you go into my book, you'll see the full proofs.